Next speaker is Professor Kamran Eshraghian. Many of you may know him very, very well. He is an outstanding teacher and a great researcher. And one of his highlights is his really textbook on principles of VLSI design or system design, which he published along with his former student, Neil Westy, when he was at the University of Adelaide, and that has become almost a Bible in system design. And I think Kamran is going to bring similar perspective on how we can do 3D integration through his expertise in his knowledge in CMOS as well as VLSI. So we have a very interesting talk. Kamran, please come. Yes. Let us welcome Kamran. Yes.
Well, thank you, Mr. Chairman. With that introduction, I'm dying to hear myself talk. Let me use this technology to get the slides down. Actually, this talk is in two parts. I'm going to give the first part, and Professor Cho from Chungbuk National University will give the more exciting part of it, actually building the circuits and systems. So if you can just bear with me getting rid of this, and one of these days with memristors we can probably change this altogether. And hopefully well, firstly, just before I start, I wanted to acknowledge quite a few people because they have been instrumental in making all of these happen. Firstly, Dr. Khan, who was invited to give a lecture in my spring class a couple of years back, and he said memristors, and I had no idea what this memristor was. And at that lecture, I get very excited. So it was very important that I do acknowledge. And then it was Hewlett-Packard, this Stan Williams group, because they published and we had no access to data. And I was very, my gratitude goes to him and his group to produce that material. And there are a few people from around the world. Now to just get the perspective right, we Australians, we have got some complexity problems. So we decided to change the world around. And it is everything's perspective, as you know. And this reminds me of a very interesting story I shared, that there were three eminent scientists from the United States, from Russia and Australia, debating their space program. The American said, well, look, we are going to send the space probe to Mars and Jupiter and come back. And of course, the Russians said, oh, you have done very well, but we are going to do something better. We are going to send the space probe to not only Mars and Jupiter, but it comes back to Venus, and we go down and scoop something and bring it back. Of course, the Australian from my university says, hey, we have solved a lot of the problems, and we are going to send the space probe to the sun. The two jumped up and said, you can't do that. You can't send the space probe to the sun. It will burn up. They said, ha, we solved the problem. We are going to send it during the night. So what I'm hoping to do is that this very learned community, that together we don't have that perception of sending the space probe to the sun. But together we can build up a community, as we did 30 years back, with many teachers who taught teachers and students who actually made CMOS happen. Because if you can identify a single thing, why we were so successful in CMOS, including the roadmap, was we had many, many teachers in a very short time that began to understand CMOS and work together. So having said that, let us look at what are the disruptive technologies. And I thought this could be a very interesting one. No, it can be a very interesting one because it is not going to work. But never mind, we'll pass it on. And again, from this symbol electron to, does this thing press? Doesn't matter. We are very happy with technology. J.J. Thomson, 1883, and we are coming towards this system on system, and I hope I took some of your good pictures. Leon and I don't know whether Dr. Stan Williams there, but it's the best I could do, and of course Steve. But the important part was it took 100 years before we got to CMOS, and in between we had some disruptions. And then, of course, 2008, we had to change path. So what I want to do during the next few minutes, really to look at how we can build up systems with CMOS mentality, because if CMOS is there, if the scaling is there, if the roadmap is there, how this disruptive technology in the form of Memristor and Memristor system can enhance building up these systems. And of course, let us look at the family of the digital ICs that invariably in this group we have been involved in some part of it. I just want to isolate a couple of things, that we had active substrate and insert substrate. And if we go down, we see the nano CMOS beginning to emerge on the roadmap that we just saw, some of the exciting part. But then we have got, yes, if we had again Memristor system, maybe that wouldn't happen. Then we have got somehow Memristor fits, never mind, would this thing work by chance? No, that won't work. No, I don't want it to go back. Anyway, what we are sort of looking at, that all of these are going to lead us in this system on system, and eventually to this intuitive systems neuromorphic that many people have got excited about. But what are the disruptive part of this system? We have got plasmonics. On this hand, the metamaterials that is beginning to emerge, the negative permittivity, permeability, and the refractive index beginning to emerge, and how these things are going to influence the operation of the systems. And I'll just give some glimmer of some of the people we work with. For example, what is the motivation? You have got these processes, they do a lot of compare. What do we do? There are the search engine tasks, the meta-security cameras of the future, the plasmonic-based laboratory on a chip, so that we are beginning to see that Memristor by itself is a wonderful thing, but if we have the opportunity to integrate the environment, they give us some new options. For example, if we look at Google, there is this 50 megawatts. So the challenge was, well, look, can I get rid of one building of heating? Maybe still with CMOS and Memristors, there are some possibilities. And then there are the data compression and identification systems, half transforms. It can extract shapes so that you need to kind of store information and in one cycle hit it and do the comparison. Huffman coding. Then there is the Lamp-Elzev compressions, that variable length to fixed length code transformers and so on. So all of these require some kind of cheap memory that can remember, and if I remove the power, it is still there, and how effective these things can be. So for example, transformation of 2D to 3D in terms of DWT, we could do it very nicely because we have two dimensions, length and width, which we could visualize, and then in this kind of transform we brought the third dimension, which was time. Now all of a sudden we see, well, in one of the lectures somewhere here, they said, oh, but we can put another 1,000 layers, so that we are already moving into the third physical dimension. So now is the whole issue of what is the fourth dimension? Configurability, which again, it brings the time factor into the picture. And then if we start bringing, this was one of the chips we designed some time back for steering beams. But we had complex problems, because if we could only store effectively the phase hologram, then we could have performed magic. We could steer the beam here in a few degrees. We could have split the power, and then we could have done the multiplexing of the wavelength. Just imagine that if we could do this as a base, using the memristive structures, and this is some of the things that we are working on in bringing the plasmonics together with memristive systems. And then here is one of the applications that the group in Adelaide are working on holy fiber. That if we have got this fiber, this is the core, and this is the fiber that we can put with all different kind of reagents. And we launch a wave, and these are very small waveguides. And then we can have a forward reflection or back reflection, which characterizes the behavior of it. Now, if we can integrate that with the base of this particular chip that we can move, then we can identify any reagents, any viruses, any DNAs in one single hit. And by our ability to create these phase holograms, so it opens up whole new possibilities. For example, we can identify the signatures automatically in this way, and these are, just imagine, sits on top of the chip, a very, very narrow channel. And we can especially build it. And then the 4 systems that people talk about, integrations is possible in terms of dynamic reconfiguration, and the whole notion of meta-logic that people work on, and maybe Dr. Cho will talk a little bit more on that. And then if we look at the multi-technology roadmap, he says, well, in the past we had nano-CMOS, Schottky, it led into numerous products. Now what happens? What are the products of the future? For example, if we have got Memristor on here and metamaterials here, if we can merge these together, what are the meta-logics, meta-senses, intuitive healthcare that some of them hopefully begin to emerge in a not too distant future. So the possibilities of the product gives us a lot of motivation to rethink the whole process of systems, particularly the 4-dimensional system, reconfigurable systems. The whole notion of 3D that has emerged in the last 2 years, system on chips, where you use through TSV to do the connections through silicon via. Now it has emerged with new possibilities. And then we come to the sandwich principle at long last, and I hope you can add that to your roadmap of the future. Because if we have got a generator, no matter what you do, there is the mobile, for example. What are the constituents? There is a generator, the power source, there is a display, and you got the engine in the middle, which is the Moore's law related. Now, with Memristor, the way we sort of got so excited about that we can possibly move this Moore's law for few more years into the future, if we can mix it with CMOS, or when we mix it with CMOS. So the idea is, how thin can we go with this? Well, first of all, I have to be able to read, unless we go on MIT sixth sense that something else can happen. And these are the kind of things that is possible. It has to be thin enough and large enough. So how does that thing map? This was the mobile technology, Nokia 63100i. It was a very large one, and with time became with a various. And then the way we see, there's a kind of a threshold that, unless this material gets pretty thick, it gives us some kind of a limit. What is the volumetric growth of these systems are going to look like? And these are the future cards that hopefully we can generate and bring us some sort of new possibilities. And maybe these are the things that if I've got a card, and for the ladies it becomes a fashion item. Just if they say, what is the time? They said, well, it is 3:23. It gives us some sort of option. Anyway, this part of the talk is going to be given by Professor Cho. My only conclusion is that we need to build up educators so that we can educate a much larger community, and the more we have, the better it is in terms of our integration and also exchange of knowledge base. Professor Cho from World Class University Program, Chungbuk National University.
Okay, thank you. In terms of system-on-system architectures, I'm going to talk CMOS and Memristor mixed-up circuit through the CAM content addressable memory design. Now we are focusing on image mappings. Images from CIS is compared with another images stored in database. CAM, content addressable memory, is a very suitable search engine to find data in our memories. This is CAM architectures. The architecture consists of cell arrays and some control circuit here. Data comes from bottom side here, and we have controls for write and read enable on left hand side. Then we get the output at here that notify us there is some data we are find. Okay, this is conventional CAM cell using SRAMs. This 10 transistor NOR type CAM here, and the other one is 8 transistor cells. Both of them are using SRAMs. So far, this 8 transistor cell is very popular for designing casing in microprocessors. Still, using SRAM in the cell, it has some problems, like area utilizations and more power consumptions. Still, we shrink this 8 transistor circuit by with improved technologies. This is Memristor-based CAM cells. We provide 4 kinds of CAM cells, 5 transistor NAND types, and 6 transistor NOR types, and the last one is 7 transistor NOR types. As you see here, there is no PMOS in a cell, which means there is no well in the cells. It is a very packed logic. Each cell has 2 memristors for data storage and CMOS circuit for data searches. They look very similar, but they have some difference. Somebody is on these tables using 3 voltage supplies. The time for programs in our memristors is 220 nanoseconds. Against that, the read time is 10 nanoseconds. It's very fast. Also, this A and C, the NAND type has some VT degradation due to the serial connection of NMOS on the matched lines. We are used type D for our design. Please look into this circuit. And we have 2 memristors, ME1 and ME2 here. Using these memristors, it gives us some area reduction, 46% than conventional ones. Also, we saw significant power reductions. It's almost 100 times than conventional SRAM type CAMs. But however, it's very slow to write in the memristors. again, despite of past read. Look at here, and this is a very similar with DRAM architectures, one transistor and one CAM to save 1 bit data. To write in Memristor, we select word line here. Then transistor M1 and M2 should be on. Then Memristor ME1, ME2 is state is decided by bit line on data on bit line. That time the VL keeps low voltage. This colorful slide shows some layout for CMOS and Memristor-based CAMs. Two Memristors are here on the metal 3 layers on a silicon. This is very smaller than conventional CMOS. To evaluate read operations, I write the data in the cell like this, and data 1 is saved in the cells. To read, we provide the VDD on VL here and search the signals here. Then these two transistors, M3 and M4, should be on, depend on the state of Memristor ME1 and ME2. It's really tricky because Memristor 1 and Memristor has some resistance, high and low. Then we supplied VL. Then we have provided very short time on here, then the M3 and M4 will be on. Then we get some result on this node, and it makes turn on MF transistors. This slide shows a simulation result. We set 2 evaluation areas here. And we provide the search signals very short times, R1 and R2. During R1, it's here, and matched line, that is output of CAM, keeps high. Then means data is matched in the cells. But on the R2, the matched line went down to 0 because we applied the 0 while the 1 is saved in the cells. This figure shows some change the memristance by the during the reading memristors. ME1, ME2 change the real memristor like this by the length of time. That means that we access many times the cell, even though it's short pulse R1 and R2, then memristor will have a chance to change it to another state. Also, we are considering simulation these memristors. But there are two types, linear and non-linear model of memristors. The window function is very useful model for circuit simulator as a non-linear model. These days, we find two types of window functions on this reference. We used this equation for the simulation that is expressed as behavioral models. Then we combine behavioral model for memristors and the model sim for CMOS circuit. And we designed a small Memristor-based CAM in a chassis for 32-bit microprocessors. 32-bit microprocessor has 21-bit tab to match data in a CAM. This is a Memristor CAM with 21-bit. We provide the data here, and we get the matched out here by control signal over on top side. Look at here. And now the data is stored 10101 on matched line 1, and the other 10100 is stored on matched line 2. When we provide 10101, the matched line 1 keeps high like this, while the matched line 2 is went down. This simulation we get combining the behavioral models with for memristors and model SIP in the circuit simulators. We confirm the Memristor-based CAM work well. I want to mention device fabrication of memristor in our design. All parameters are from HP papers. As a first step, we deposit titanium oxide on silicons. The target was controlling oxygen de-efficiency to 5%. On this table, the first sample shows oxygen de-efficiency is 1.85%, but the second one is almost at almost even state. But and as a result, I think it's possible to control oxygen de-efficiency in reasonable variations. We fabricate the device in the future. I'd like to summarize my talk. We introduced CMOS and memristor mixed-up circuit design through the CAM designs. And we are focusing image mappings, and then we can expect to expand this kind of memristors for the image data searches. And the images from image sensors, then we get some charge amount at the output of image pixels. Then the all amount of charges can drive the memristor directly. Then it just same with us to control memristor as an analog device. Then we can store the analog data in the memristors. We believe the kind of technology comes earlier soon. And also CMOS and memristor mixed-up circuit provide interesting solutions. And we consider circuit simulation, combining behavioral models and model scenes for the mixed circuit. But now designers need to work understanding physical domain. But considering all these situations, the Memristor is a very disruptive technology, but it is now a possibility within present technology. Thank you for your attention.
Thank you, Professor Cho. This is for you and Professor Kamran Eshraghian. It's very, very exciting. Thank you. Thank you. So I'd like to